Okay, this is lesson 1 of the reactions of inorganic compounds in aqueous solutions topic. The topic follows on directly from the transition metals, and much of what you've learned there will be absolutely essential for what you're doing in this. What I would like you to do is go through listening to the video. When it asks you to pause, that gives you the opportunity to try the task for yourself. And then once you've tried it, you can go ahead and review and find out how well you've done, and if there's anything that you need to dig into a little bit more and get some more understanding and clarity on the topic. So let's begin. And we are taking a look once again at something that's very familiar. As I've said, it's metal aqua ions. We can see the one at the bottom here, and as the blue box says, having that knowledge of transition metals is absolutely vital if you're going to come into this topic ready to understand what we're doing. So to begin with, we're going to remind ourselves that when we talk about, for example, aqueous copper ions, it's not as straightforward as we might have learnt at GCSE. And actually, an aqueous copper ion is a copper ion that's surrounded by 6 water molecules, as we can see down below. So your first task is to identify what we would call the shape of this hexaaqua ion and what the bond angle would be. So pause. And now you've had a chance to do it, let's take a look. Now you'll remember from shapes of molecules that there are many different shapes and bond angles that you need to know. We're actually quite limited when we get to the transition metals topic, how much of it you need. This is the most common one. It's an octahedral structure and the bond angle is 90. The other ones that you are likely to have to talk about are tetrahedral, and that's when we have chloroligands, and we would also be needing to remember, in the case of silver complexes, linear with a bond angle of 180. Okay, so for the next task, this is a good opportunity for you to get to grips with drawing out these complexes. So have a go, try to draw out the ion, the FeH2O6 2+ and FeH2O6 3+. Pause. And my technique for doing this, and what I would recommend you do, is always start when you know that it's octahedral with the central metal ion and draw the 6 lines coming away from it. Now you might draw these 3D. It's less commonly required when you are doing complexes, but it's not to say that they wouldn't ask you to draw the 3D structure. Once you've done this, you can add the waters. And I've added them on, and so far these are looking identical. You will notice that the bond goes from the Fe to the O. That is absolutely vital in what we're doing on here. So certainly don't just write H2O on the right hand side, for example. That will be saying the Fe is bonded to an H, which is a chemical error. Now, because these are ions, we need to represent the fact that they're ions. We use square brackets. Square brackets here does not mean concentration in moles per decimeter cubed, but it is still vital that these are square brackets here. And then we add the charges. Now, we know on the left-hand side we have an Fe+2 ion, and on the right-hand side we have an Fe+3 ion. We also know that water has a charge of 0. So for that reason, the charge on the complex is equal to the charge on the central metal ion. Okay, we're going to move on, and we are going to now start to consider the acidity of complexes. So we're starting to now look at the reactivity of them. This takes us right back to year 12 though. I want you to think about these questions. Do what you can to answer them, comparing Fe+2 and +3. Pause. And now you've had a chance to answer them. So we are looking at Fe+2 ions and Fe+3 ions. How are they going to compare in size? Well, Fe+3 is smaller. And it's important that we know why that's the case. We've got Fe, whether it's +2 or +3, the number of protons in the nucleus is identical. But in an Fe+3 ion, there's one less electron. That means that that positive nuclear charge has a stronger attraction to the remaining electrons and it pulls them in. The second question, hopefully much more straightforward. How do they compare in charge? Well, the Fe plus 3 has a higher charge than the Fe plus 2. Not really a lot more to say on that. Now, what we then need to do is consider charge to size ratio, and this is what's going to be really important to us. And if I've put this at the top actually so you can see, with the Fe plus 3 it has a higher charge and it has a smaller size, so it has a greater charge to size ratio. That's the Fe plus 3 ion compared to the Fe plus 2. Okay, the remaining questions are related to the diagrams that we've got here. And you can see, you drew these earlier. This is done as display formula, and it's also representing the fact actually that there are coordinate bonds or dative covalent bonds whereby the O's in the water are donating both of the electrons to the bond with the Fe. Now, the questions that I want you to consider have now appeared on the right. I want you to think really carefully about these. Have a go at them. Pause. And we're now going to start to go through the answers. So we're going back to our basic knowledge of acids here. What are they going to donate if they're acting as an acid? And acids are proton donors. That's the Bronsted-Lowry definition. It's not the only definition, but it's certainly the most common one. So when we think about what's going to happen to FeH2O6 plus 2, and it's going to donate a proton, what's it going to look like? Well, one proton going means that instead of an H2O, we have an OH. So we have got FeH2O5 OH. But that's not the end of it, because actually OHs, hydroxides, have a -1 charge. So the charge on the complex is now going to be different. My Fe is plus 2, my OH is -1, so my overall charge is +1. And it's also aqueous. We're going to talk a little bit more about why it's aqueous as we carry on through this topic. If we do exactly the same thing now with our FeH2O6 plus 3, very little different. The only difference here is that we are going to end up with a +2 charge on the overall complex when one OH is formed. And I've added on both of them here that we have a secondary product, which is the H+, that's being donated. Which of these is more likely to happen and why? This is the most likely one, the FeH2O6 plus 3. And the reasoning behind it, it's really important that you understand. So let's try and break it down a little bit. The Fe plus 3 is smaller and it's more highly charged. So what that means is that it can actually withdraw electrons towards itself, and part of that involves attraction of electrons from the OH bonds themselves. And if those electrons are moved away from there, that essentially weakens those bonds. Now let's look at that in diagrammatic form. We go back to these diagrams and you can see there's an extra bit that's being added. These electrons being attracted to the Fe plus 3 and then moving along in this direction. Now that weakens OH bonds. It makes it easier for the complex to lose an H+. I think it's really important that we recognise that this is something that is happening in aqueous solution. We're not adding anything to it, but it can donate a proton. And we're going to look at reactions that are going to make this happen more later on. Okay, moving on. And the blue box really summarises what we've been looking at. If we have +3 central metal ions, they are always more acidic than +2 ion in the middle of a complex. So how else can we represent this reaction? To begin with, we need to remember that H plus ions don't actually exist. So I want you to have a think about this question. What would be formed if an H plus ion reacts with water? Pause. And we're simply going to add together what we've got here. The H plus aqueous reacts with H2O liquid. Please remember that H2O is liquid, not aqueous. Aqueous means dissolved in water. Water doesn't dissolve in water, so it's L. And when you put those together, you end up with H3O+. Now, you'll learn about those in the acids and bases topic in much more detail, but that's the oxonium or hydroxonium ion. And that is also aqueous. And whenever we talk about an H plus ion, we really mean H3O+ ions. We're just simplifying it. Okay, moving on to the next questions. So we have been thinking about what would happen to complexes, whether it's a +3 or a +2 central metal ion. In this case, we have got a +3. We know they are more acidic, and we've got the diagram, or we've got the equation, that represents what will happen. But I want you to have a think about what will happen if we then add hydroxide ions to the complex. And we're going to look at it stepwise. So what would happen if we added one OH minus, and then what would happen to the product of that if we added another OH minus? So have a think about it, pause. And now that you've had a chance to think about it, let's take a look at the equation. So we've already gone to MH2O5OH, and that's +2. And we're adding an OH minus. Now you can look at this in one of two ways. It looks like the OH is simply replacing a water. But actually what's happening is the OH minus is coming along and taking another hydrogen from another water ligand. And that's why we end up with the H2O there. Now if I then take my MH2O4OH2 plus and I add another OH minus, I end up with this. And you can see I've added the state symbols on there now. So we had aqueous, 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 liquid for water for reasons that I've already discussed. On this one, what are the state symbols going to look like? Well, the key difference here, and I've highlighted it in red, is that my complex is now solid. We really need to understand why it's solid, and that will actually help you to remember some of the numerous observations that you're going to have to make. So let's take a look. Here are the equations once again. Why do we think the reaction stops at this point? So have a go, pause the video, and now you've had a chance to think about it. The complex is no longer charged, it's not ionic, therefore it's insoluble in water. Remember, ionic compounds dissolve in water. This is no longer ionic. So because it's not dissolved in the water, it can't react further. And it stops. And that's going to be true for any +3 aqua ion. It will stop once we reach a neutral solid complex. Moving on. We're going to look at what happens with MH2O6 +2. So I'm going to pause and I want you to think about how far that will go. Be really, really mindful of the state symbols as you go through. Pause. And I'm going to jump straight in to look at both of the equations here. So we're starting with our +2, we add the OH minus, and we end up with a +1 complex, as we can see here. When we add an OH minus one to that, here we end up with our solid complex when we've reached H2O4 OH2. And you can note there the solid state symbol because it's no longer charged. Now, key word here, we've made a precipitate. So we can now start to identify equations where a precipitate will be formed. That's going to be hugely important as we carry on through this topic. Let's take a look at some examples. I want you to go through each of these and finish the equation. So pause. And I'm going to jump straight in here with the answers to the first four. In each of them, you can see that we have replaced one H2O with an OH and we've made an H2O. Exactly the same as we've done in the previous examples. I think in every single one of these, you can see that we have got aqueous complexes. We have still got charged complexes. Moving forward to the final three answers. This is a combination of the stepwise equations that we looked at earlier. If I add 2OH minus, I can show that in a single step. I'm remembering that I've made 2H2O. And what's important on this one is that you can see that these are solid, and in both of those situations where I've highlighted the state symbol, that is where the reaction would stop, because we've got a solid complex, it's no longer soluble, and the reaction cannot continue further. Finishing off this particular lesson, we're going to introduce the idea of carbonate ions and what happens to them if I put them with +3 complexes. And this is just introducing the idea. We're going to build on this a lot in future questions. But I want you to read this, answer the questions after you've paused, and then we'll look at the answers. So pause. And for the first answer, we're going all the way back to key stage 3, the general equation as a word equation. If I take an acid and a metal carbonate, I make salt, water, and carbon dioxide. And we actually use this as the test for carboxylic acids. If I have something that I think is a carboxylic acid, I add a metal carbonate to it. If it effervesces and I then bubble gas through the lime water turns cloudy. So, going to stop at that point. We will continue with this in the next lesson. Any questions, please do make a note of them and ask where you can to get the information that you need. And we're done.